Hey there, welcome back to the channel. Today we're going to start on our series of turning this microcontroller into a temperature sensor that turns on a fan for our dart. First thing we need to do is figure out how to get a temperature from this into here and calculate what this guy needs to be. Let's get to it. If we're going to build a microcontroller that reads automotive sensors, the first thing we really need to understand is how automotive sensors work. There are generally two types. One type provides a variable resistance across its sensing range, and the other provides a variable voltage across its sensing range. In this case, we're going to be working with temperature sensors, which are these, and they typically provide a variable resistance. This is a manifold absolute pressure or MAP sensor. This provides variable voltage. You can generally tell if they've got more than two connectors. So if it has one connector for a wire or two, it is probably resistance. If it's got more than two, it is probably voltage. It's not always the case, but it's a general good rule of thumb. This is a Mopar style, old style. Takes a single wire on here, and then it grounds through the block of the motor. And basically what we do is we provide a wire here, and then this provides resistance to the block. You can see it's kind of insulated here. So it provides a resistance through this based on temperature. This one, which I think is a GM style, it's got two wires, so instead of grounding through the block like this one, it has a wire that provides voltage and then a return back to the computer. They both work effectively the same way. Since we know these vary resistance, or at least we strongly suspect that these vary resistance with temperature, we need to profile that. Now, I've looked online at some charts trying to find what is the chart for this, but it's really not easy to tell. I see some that have in the hundreds of ohms. I see ones that have in the thousands or tens of thousands of ohms of resistance. So the easiest way to do this is for us to just test it, right? The range isn't very big. It's from, room temperature, or I guess cold in the winter, up through probably about 220 degrees. So the best way to do that is we're just going to drop it in a kettle and then raise the temperature on this and measure the resistance across it. Then we can use something like Excel to give us a graph of what that looks like. The first thing I'm going to do is I'm going to set up a table so that I don't have to be rushing when I'm writing. We're going to call this the GM style. And I'm just going to do a list of, let's call it 5-degree increments. That should be enough, and if I miss a couple, then that's fine. That should be good enough. Temp. The next thing we need is an ohmmeter. A standard multimeter would work fine. This is just what I've got handy here. This does ohms. This one also does the typical beeping. If it's got continuity, we don't need the beeping, but this will work. This sensor has a Delphi connector on it, so I made a pigtail here. If you're interested in how these clamp together and how these work, just leave a comment down in the comment section. I can do a video on that. But effectively, we're just going to plug those together, drop this down into the kettle, and then hook up the meter to the other end of these wires so that we can watch resistance, turn on the kettle, and then write down some values. Nicely, this meter has little clamps that I can just put on here. Makes my life easier. And we can clamp it onto the wires. You can see we have infinite resistance at room temperature. Not unusual, because for a coolant temperature sensor, room temperature doesn't really matter. If you had like an air charge sensor, something that goes into your intake manifold that's measuring the temperature of the air coming in, that will give us a reading at this temperature. It will give you a reading all the way down to, I don't know what the low end is, but I would think sub-zero anyway. Take the sensor and drop it in. I don't want it sitting all the way down at the bottom, because then it'll be sitting on the heating element. I want it kind of just floating up here at the top. And you can see the end is just kind of floating around in there. And I have an instant read thermometer here that we can put in there. And it says this water is about 70 degrees. So we're going to turn on the kettle, start watching this, and as this comes up past these values we have here, I'll write down the value that I see here. And I'll try to do this without being in the way of the camera. I would have expected it about 120 or so, typical gauge range. Oh, there it comes. About 650. Look at that. And we're now at a rolling boil. You can see that it was infinite for a long way, and then starting at about 145 degrees, these are all ones, we started to actually have some resistance other than infinite. And it was fairly linear, but then it changed. We'll graph these out, but you'll see that it looks like it's maybe logarithmic, or it doesn't really matter. What we could do is you'd have two different options here. We could just do a lookup table. This is obviously just for a car. We're not really all that concerned about our coolant temperature down to the 10th of a degree. Even within 5 is probably fine. And you could just do a lookup table in your code that said, oh, if I get 231, I have 200 degrees. But we'll at least do some math, just might as well. Now we could actually go on the downward side as well and write these same things in, right? So we could get second temperatures for a lot of these. We are right now at 205. Yeah, we're still at pretty high. So 206 is 203, right? So we could add some other ones. 206 is 203. 205 is about 204. More data gives us a better curve. It's just much, much slower going in the downhill direction. If you were extremely patient, we could let this cool back down and write down these values as it cooled back down. I don't have that kind of patience, I don't think. These should be good enough. And you can see, I did have patience. As it's heating up, it comes up really, really rapidly, so I don't know if we've got good mixing, if the temperature at the probe is the same as what I'm getting here. Going back down, it's a much slower process, so I can get these temperatures. I think they're probably more accurate. Takes a lot more time, but profiling as it cools is a much better route, I think. We can do a separate chart for this style. Hopefully it'll have the same curve. If not, if it's got its own curve, we can make our code allow us to select the type of sensor we have, or even select the curve. Alright, so fair warning. We're going to start talking about some math. I know, a lot of people dislike math, it's frightening, whatever. We're going to keep it at very basic algebra level, Not going to do much of it, and the stuff that we do, most of it we're going to use the computer for. It's a good thing to have at least some fundamental understanding of the math that goes on here. Again, it's not hard, don't let it scare you. We've profiled this guy, and we know that it has some resistance across here, so it's acting as a resistor based on temperature. We have a microcontroller. This is a Meadow F7 from Wilderness Labs. This is what we're going to be using for making our device. And so this has analog inputs, and it has some power output. We know, using a thing called a voltage divider, that we can send this out through a resistor and through the sensor, and then back into one of these analog inputs and get a voltage. Let's take a look at how that looks. Over here we have our microcontroller, and here we have 3.3 volts, and this is called V in, so voltage in, and this would be our analog input into the microcontroller. We'll just call this A0, and this is the voltage out of our voltage divider. So we're going to send in 3.3 volts and then read back some value less than that based on the resistance of this sensor. The first thing we do is we go through a fixed known value resistor. We'll call this R1, and then we go through our sensor, which we know is basically a variable resistor. So we've got this resistor here, and then it goes down to ground. And this is our sensor. We'll just call this R2. And then if we tap right here and bring that back into our analog input, this voltage will change with the value of this resistor. So this is what we have to build. There's a little bit of protection logic that we're going to put on here, but from a perspective of how it works for reading in the value of this sensor, this is all we need. Now the relationship between this V out, V in, and these resistors is, again, here's that math, here's the formula. Our output voltage, this one, is equal to the input voltage, the 3.3, times our sensor voltage, divided by this one plus this one. What this tells us is this gives us a relationship between all of these and what we're going to read. Now, we're going to be reading in our software a voltage, but that doesn't give us much use because we know from our math, from our chart, that if we know the resistance here, we know what temperature it is. We don't have a way to convert directly from voltage to temperature, just from resistance to temperature. So what we really need to do is, if we know this because we're reading it with the microcontroller, we know this because it's fixed, we know this because it's a fixed resistor, and then how do we calculate this? So it's just some simple algebra. We'll rearrange this. I'm not going to show all the steps because, well, we're not in school, and you don't have to show your work. The reality is I cheated and looked it up. So this sensor resistor, R2, the resistance here, is our V out times R1, all divided by our input voltage minus our output voltage. So these two formulas are what we're going to use to calculate what we need here and to calculate what the value here means for this. So the next thing we really need to figure out is what fixed value resistor here will work best for the range of values that we have here and our known good 3.3 volt source voltage. Now, mathematically, we could do this on paper, but let's go over and do this in Excel instead. Let it do all of the work for us. Because this really isn't a lesson in using Excel, I'll just kind of describe what I've done. I put in all of the data that we gathered here. This is for the GM style. And I actually did it also for the Mopar style. I then created a plot for each one. And then I run a best fit line here. And then from that line, I got out this equation. And this is a power equation. So if we look at this, I selected a power equation. This is the equation that we're going to use to determine what our temperature is given a resistance. I then went over here and decided, okay, we need to figure out what our resistor needs to be. What is the fixed resistor? So again, I entered in all of these values, and then I used that formula that we looked at for getting voltage from a resistance. So given this resistance, the estimated voltage would be here. Then I did a full table of those. Now, to get the best readings possible, we want the largest range that we can have here. So I actually started out with a 470 ohm resistor, and this number here is the, as you can see, it's the max minus the min, so it's the total range here. So at a 470 ohm resistor, we have almost a volt change, 0.97, but a 330 gives us 0.99. So this is really the closest with a standard off-the-shelf resistor. So a 330 ohm resistor is what we'll use for our fixed resistor, for R1 in that equation. You can actually see that it gives us the best on the Mopar sensor as well, which is really good. So now I came over here and did a check on the math. Again, these are the resistance and temperature that we recorded. Then these are the estimated values. Basically, it's these values from that equation rounded to 2 decimal places. And so then I take this and I plug it back into the equation that goes in reverse and say, okay, if I'm given this voltage, what is my estimated resistance? This column here and this column here are, as would be expected, about the same, because I'm just basically moving one direction, cropping the decimal, and then going back. This is the calculated temperature. So this is taking, oh, and look at that, there's a bug already. Let me do that. Oh, that's much better. Okay, so this is that equation right here that we got from having this best fit line run. So then I take that equation and I take this calculated resistance, plug it in, and this gives us a temperature based on this resistance. So it calculates that given this resistance, this is what it thinks the temperature is. This is what we recorded the temperature at that resistance. And so this column shows us how far the calculated is from what we recorded. And you can see, just scrolling down through these, you know, this is a third low, 1.3 low, 1.3 high, that sort of thing. They're all within really less than 1 or 2 degrees except this very first one, and the average is only a half a degree off. So if we use that formula and a 330 ohm resistor, the simulation, or the model anyway, shows that we should be within half a degree of actual based on our calculation. So that tells us we have everything we need to build up a prototype of this. So the next thing we'll do is we'll build a breadboard with that 330 ohm resistor and run it. We'll use that resistor and that formula and read the voltage, convert it to basically a resistance, which then converts to a temperature. Basically, we'll throw it back in the kettle. We'll check the output of our code and our formula and our voltage divider against what we actually are reading with a thermometer. We'll use the InstaRead again. If the breadboard works out, we'll move forward and actually design a PCB for it. Those will be upcoming videos. There you have it. Thanks for watching.